Before we kick off this deep dive, just a quick heads up. The voices you're hearing today are powered by AI. We've optimized this content specifically for your listening experience. Okay, let's unpack this.
Today, we're doing something a bit like a critical code walkthrough. Imagine we're staff engineers presenting to the team,
Right.
we're dissecting this really foundational piece of infrastructure, something many of you might use every day without even realizing it's there. We're talking about LevelDB,
Ah, LevelDB.
a super fast key value storage library from Google. It's an essential building block, just quietly doing its job under the hood.
Absolutely. And our mission today really is to explore LevelDB. We want to look at its core functions, some unique features, but also its, limitations.
Right.
Crucially, we want to understand the design choices that make it so performant and why it's so widely used.
Okay.
And for anyone maybe less familiar, a key value store, it's basically like a super efficient dictionary. You store data using a unique key, and you use that key to get the value back super fast.
So we're essentially pulling the key insights straight from the original LevelDB GitHub docs, giving you a shortcut to understanding this pretty powerful library.
Agreed. So, laying the groundwork then. The docs describe LevelDB as a fast key value storage library. What does fast actually mean here? How does it, achieve that speed?
Yeah, fast isn't just marketing fluff here. It's fundamental. LevelDB basically gives you an ordered mapping, string keys to string values.
Okay, ordered mapping.
Exactly. And it was written by Sanjay Ghemawat and Jeff Dean at Google.
Ah, okay. The names tell a story.
Right. So it was designed from the get-go for raw speed and efficiency. And it's an embedded library, which is important. It runs inside your application, not as some separate server.
Embedded.
And the speed, a lot of that comes from its core architecture. It uses something called a log-structured merge tree, or LSM tree.
LSM tree. Okay, heard of that.
Yeah. And that design is really optimized for high write throughput. See, new data goes into an in-memory thing called a memtable first, sequentially.
In memory, okay.
Then, only later, it gets flushed to disk into these immutable sorted files. They call them SSTables.
SSTables, got it.
This whole append-only approach, it minimizes random disk I/O, which is notoriously slow, making those writes just incredibly fast.
That makes sense. So the LSM tree is key, prioritizing fast writes by sort of buffering and batching in memory before hitting the disk in this optimized, sorted way.
Exactly.
And it's also important to flag, isn't it, that LevelDB, well, it's under pretty limited maintenance these days.
That's a really crucial point, yeah. Anyone thinking of using it needs to know. The project mostly gets fixes for critical bugs, data loss, memory corruption, that sort of thing.
The serious stuff.
And changes that are absolutely needed for Google's internal teams. So, look, it's stable, it's robust, but it's not actively looking for lots of new features or, tons of outside contributions. It's more about keeping it solid in its specific niche.
Understood. Stable, but not rapidly evolving. So, with that context, let's talk features. This is where it gets really interesting. LevelDB isn't just a simple box. It has some pretty powerful tricks up its sleeve, right?
Oh, yeah, definitely. Despite aiming for simplicity, the feature set is pretty robust. First off, keys and values. They're arbitrary byte arrays.
Meaning not just text strings.
Exactly, not just text. You can stuff anything in there, serialized objects, image, data, whatever.
Yeah.
That flexibility is, it's fundamental. And like we said, the data is always sorted by key. That's the LSM tree foundation.
And that sorting, it's not just fixed alphabetical, is it? You mentioned customization.
Precisely. Callers can actually provide their own custom comparison function. This is super valuable if you're dealing with, say, different character encodings or maybe complex data types where simple bot comparison doesn't cut it.
Ah, okay. That's powerful.
Then you have the basic API. Put a key value to add or update data, get key to fetch it, delete key to remove it. Pretty standard stuff, your bread and butter operations.
Okay. But with all this stuff happening, right, background compactions from the LSM tree, how does it keep the data consistent? Especially if I want to change multiple things at once.
Good question. That's where atomic batches come in. You can bundle multiple changes, puts, deletes into a single write batch.
Ah, like a transaction.
Kind of, yeah.
Okay.
Atomic. So either all the changes in that batch succeed or none of them do. This prevents your database getting into some weird, partially updated state.
Makes sense. Consistency is key.
Definitely. Another really neat feature is creating a transient snapshot. This basically gives you a stable point-in-time view of the entire database.
So like a photograph of the data.
Exactly.
Yeah.
It's incredibly useful if you need to do a long read operation, maybe scan a lot of data, and you don't want concurrent writes messing with what you see. You effectively freeze the state for your read, but writes can keep happening in the background.
That is elegant. Doesn't block writers. Okay, so you've got your data in, maybe taking a snapshot.
Yeah.
How do you actually move through the data?
It supports both forward and backward iteration. So you can easily walk through your key value pairs forwards or backwards based on the key order.
Nice.
Plus, it has automatic compression built in. It uses Snappy by default fast compressor from Google. SSTD is also supported now.
And compression helps how? Just saving disk space.
Mostly space, yeah, which is great, but often it actually improves performance too, because you're reading less data off the disk for the same amount of logical information.
Right, less I/O. Clever. Okay, what about interacting with the underlying system, the OS? Any flexibility there?
Absolutely. This is quite advanced, but all the external stuff, like file system operations,
Yeah.
it goes through this virtual interface called N.
N for environment?
Exactly. It means users can actually plug in their own implementation of how LevelDB talks to the OS. So you get a lot of control, maybe for testing or running in unusual environments. It's a powerful abstraction.
Okay, that covers the strengths pretty well. But like any tool, it's just as vital to understand what it isn't good for. Where does LevelDB maybe fall short, or what are its intentional limitations?
Right. This is critical for deciding when to use it. First big one, this is not a SQL database, period.
No tables, no joins, no SQL queries?
None of that. No relational model. No built-in support for secondary indexes or complex querying beyond just the key. If you need that stuff, you either build it on top yourself, or, more likely, you need a different kind of database. It's a key value store, pure and simple.
That's a fundamental distinction. Easy to get wrong if you just hear database.
Very easy. Another huge limitation, only one process can access a specific LevelDB database at a time.
One process. So multiple threads in one app are okay,
Yep.
but not two separate applications hitting the same files.
Exactly. Multi-threading within a single process is fine. But two different programs trying to open and write to the same LevelDB database files concurrently? Nope. That's a core design choice. Simplifies things internally, boosts performance for that single app, but it's a major constraint for, say, distributed systems.
So definitely not a shared network drive kind of database out of the box.
Not at all. Which leads to the next point. There's no built-in client-server support. It's an embedded library, remember?
Right. Runs in your app.
So if you need remote access or multiple clients connecting over a network, well, you have to build that server layer yourself, wrapping LevelDB.
Okay, so you're responsible for the networking part.
Totally. Understanding these limits, not SQL, single process access, no built-in server, it's crucial. Helps you make the right architectural choices and avoids trying to fit a square peg in a round hole. It's brilliant for its niche, but you got to know the boundaries.
Great points. Really clarifies the use case. Okay, so if someone's listened this far and they're thinking, all right, I see the niche, I want to try this. How do they actually, get their hands dirty? Let's quickly touch on building it and maybe the main interfaces they'd use.
Sure. Getting the code is standard stuff. Git, clone, recurse submodules. You need the submodules.
Right.
Building uses CMake. Pretty standard for C++ side. Works on PODKEX systems, Linux, Mac OS, just mkdir build, cd build, cmake, make. And on Windows, it generates Visual Studio projects. Familiar territory for C++ devs.
Okay, standard build process. And the API itself. If I'm writing code using LevelDB, where do I start? What are the key header files?
Good question. The main entry point is include levelbdb.h. That's where you open the database, do your put, get, delete.
db.h, okay.
The core. Then there's options.h.
Mhm.
This lets you control behavior, things like caching, compression, creating the database if it doesn't exist, error handling, lots of knobs to tune.
Options for tweaking. Makes sense.
If you need that custom sorting we talk about beyond simple byte comparison, you'll use comparator.h.
Right, for special key types.
For iterating through data, scanning ranges, that's iterator.h. And for those atomic batch updates, write batch.h is the one.
The right batch we discussed.
Yeah. There are also some useful utility headers. Size.h is quite important. It's a simple, efficient way LevelDB handles pointers to byte arrays, basically a pointer and a length. Very common in the API.
A slice of data. Okay.
Status.h defines how errors are reported success, not found, corruption, I/O errors, etc. Standardized reporting. And nv.h is that OS abstraction layer we mentioned.
It's an environment abstraction, right?
The other headers like table.h and tablebuilder.h, they deal with a lower level SSTable format. Most users probably won't need to interact with those directly.
Got it. So dbh options.h, iterator.h, writebatch.h, those are the main ones to focus on initially.
Pretty much, yeah. That gives you a good handle on the main interaction points.
Perfect. That maps out the API nicely. Okay, let's pivot to the numbers. Performance. Because for a library build as fast, the benchmarks are where the rubber meets the road, right? The docs have some results from their TerBench tool.
They do, and they're quite revealing. The setup they use is worth noting. A database with 1 million entries. Keys were 16 bytes, values were 100 bytes, but they compressed down to about 50 bytes on average.
Okay, 1 million keys. Decent size.
Yeah, total raw data size around 110 millibyte, but the actual files on disk were closer to 63 millibyte because of compression. And critically, these benchmarks generally reflect performance when the working set fits in memory. That's LevelDB's sweet spot, thanks to caching and that LSM design.
Right, in-memory performance is key. So what did write speeds look like?
Pretty impressive. Sequential writes, FilSec, clocked in at about 1.77 microseconds per operation. That's roughly 63 millibytes per second.
Wow, okay.
Random writes, FilRandom, were a bit slower, around 2.46 microseconds per op, about 45 millibytes. Overwriting existing keys randomly overwrite was similar, 2.38 microseconds per op, 46.5 millibytes.
So doing the math, that's hundreds of thousands of writes per second.
Exactly. The key takeaway is you're looking at something like 400,000 writes per second potential.
Yeah.
That's the LSM tree paying off buffering in the memtable, sequential appends initially.
But there was a slower one too, right? FilSync.
Ah, yes, FilSync. This forces a sync to disk after every single write. Much, much slower. About 268 microseconds per operation. That's only 0.4 millimeters, tested over 10,000 ops.
Okay, 268 microseconds. Wait, the docs highlight something interesting there. That's like 0.3 milliseconds, which is way faster than a typical disk seek, maybe 10 milliseconds. What's going on there? Is the disk lying?
Huh. Well, sort of. That's a really astute observation in the docs, and a practical warning. The suspicion is that the hard drive itself is caching the write in its own buffer. It tells the OS, yep, got it, before the data is actually physically safe on the platter.
Ah, the drive zone cache.
Exactly. So it looks fast, but if the power goes out right then, poof, that data might be gone, even though LevelDB thought it was synced. So FilSync gives you the option for durability, but you need to be aware of whether your underlying hardware is truly making it durable immediately. Trade-offs.
That is a very important caveat for production systems. Okay, fascinating stuff on writes. What about reading the data back? How does the LSM structure affect reads?
Reads are interesting. Performance can vary depending on a few factors. Right after a bunch of random writes, before background compactions have tidied everything up, random reads, read random, took about 16.7 microseconds per op. That's roughly 60,000 reads per second.
Okay, 60K readsec baseline.
But sequential reads, readsec, blazing fast.
Yeah.
0.48 microseconds per op over 230 millibars.
Because data within those SSTables is sorted. Reverse sequential, read-reverse, was also very fast, around 0.72 microseconds, 150 millibars.
So sequential scans are super efficient. Makes sense with sorted files. And you mentioned compactions tidy things up. Does that help random reads? It absolutely does. These compactions merge and reorganize the SSTables. After they run, read random performance improved noticeably in the benchmarks, down to about 11.6 microseconds per op. So now you're closer to 85,000 random reads per second.
Better, so background maintenance helps read speed.
Definitely. But here's the real kicker, caching. If you give LevelDB enough memory to cache the uncompressed data blocks.
Ah, keeping the actual data, not just the compressed form, in RAM.
Exactly. Performance jumps again. Before compaction with the cache hot, read random hit 9.8 microseconds, 100,000 reads sec. But after compaction with uncompressed blocks cached, read random dropped to an amazing 5.2 microseconds per operation.
Wow, 5.2 microseconds. That's almost 190,000 random reads per second.
Yep, nearly 200K random reads a second when the data is effectively served from memory. It really drives home how critical memory and caching are for getting the most out of LevelDB, especially for read-heavy workloads. The difference between disk and RAM is stark.
Absolutely stark. It's a clear demonstration of the engineering focus optimized heavily for the case where the active data fits in RAM.
Precisely. These numbers showcase LevelDB's speed when you operate it within its intended design parameters.
Yeah.
Get your working set into memory, let the LSM tree do its thing, and it flies.
What an incredible deep dive. Seriously.
Yeah.
We went from the basic idea, the LSM tree magic, through the features, the crucial don't use it for this and limitations, how you'd actually build and code against it, and right into those performance numbers.
Yeah, that could a lot of ground.
It really paints a picture of LevelDB as this foundational, highly optimized piece of kit for local key value storage. Powerful, despite its specific constraints.
Absolutely. And this whole exploration really underscores those engineering trade-offs, doesn't it?
Huh.
Performance versus flexibility, simplicity versus features. It leads to a bigger question, maybe for you, the listener, to think about.
Oh,
Well, in today's world, dominated by massive distributed databases, cloud services, what's the enduring value and maybe the challenges of a potent embedded key value store like LevelDB? Where does something like this still fit in the grand scheme of data storage going forward?
a great question to ponder. Where does focused local performance still win out? Something for everyone to consider in their own architectural thinking. Well, thank you for that fantastic walkthrough. And thank you for joining us on the deep dive. Until next time.